Birds face a severe osmoregulatory paradox. They must master extreme water conservation to survive the closed-shelled egg and the high evaporative demands of flight. To solve this, avian physiology discards the mammalian standard of a heavy liquid storage tank entirely. Birds completely lack a urinary bladder. Instead, their internal plumbing is routed through highly lobulated, tri-lobed kidneys, tucked safely deep within the bony cavity of the syn-sacrum. Without a bladder to act as a holding vessel, the ureters transport waste downward and deposit it directly into the lower intestinal tract, specifically the cloaca. This creates a physiological puzzle. Birds lack the massive medullary thickness typical of desert-dwelling mammals, yet they survive in arid environments with nearly identical water use outcomes. They achieve these results through a unique structural adaptation, the presence of an entirely secondary blood delivery network feeding into the renal system. This architecture functions as a specialized triad of hybrid filtering units, portal hemodynamics, and deep gastrointestinal integration. This kidney lobule diagram shows how birds spatially organize their filtering nephrons. Loopless reptilian-type nephrons, labeled R, reside strictly within the outer cortical band. Conversely, looped mammalian-type nephrons, labeled M, originate deeper, their loops plunging into the central medullary cone. This image provides a direct comparison of the filtration barriers for these two nephron types. On top, the simple loopless glomerulus displays a basic capillary structure, while the looped glomerulus below forms a dense, complex cross-branching network. This physical heterogeneity dictates the kidney's operational strategy. When a bird is fully hydrated, it uses all of its nephrons for rapid fluid filtration, but during dehydration, the bird selectively shuts down the loopless nephrons to prevent excess water loss. This shutdown is triggered by arginine vasotocin, or AVT, an antidiuretic hormone. As extracellular fluid osmolality rises, AVT constricts the afferent arterioles supplying the superficial cortical nephrons, reducing their filtration rate. By selectively disabling the loopless units, birds instantly toggle their renal system between high-volume fluid throughput and deep, loop-driven medullary water conservation. This diagram illustrates the vascular layout of the avian kidney. While mammalian kidneys rely strictly on a single arterial blood supply, birds feature a complex dual afferent system that integrates venous blood directly into the renal architecture. The primary arterial pathway operates much like ours, delivering high-pressure blood into the glomeruli to drive the glomerular filtration rate, or GFR. As we established, dehydration prompts AVT to constrict these specific arterioles. This drops the glomerular filtration rate and halts arterial blood flow to the cortical nephrons. This creates a problem. If arterial blood stops flowing to these nephrons to conserve water, the surrounding tubular tissue risks hypoxia and cell death. The evolutionary solution is the renal portal system. Looking at the lateral edges, venous pathways route low-oxygen blood from the legs directly back toward the kidneys. This flow is controlled by a smooth muscle sphincter, the renal portal valve. When the portal valve is open, venous blood from the legs bypasses the kidney entirely, flowing straight to the vena cava. When constricted, it diverts laterally, flooding the low-pressure peritubular sinuses surrounding the cortical nephrons. The portal system acts as a built-in failsafe, ensuring the tubular machinery remains alive, perfused, and functional even when the primary filtration engine goes into standby. Tubular tissue survival involves active cellular work that continues even in the absence of arterial filtration. Their baseline function is continuous. The deep medullary loops actively reabsorb sodium. This creates a steep osmotic gradient that pulls over 95% of the filtered water back into the bloodstream. Reclaiming water is only half the kidney's job. The other half is removing toxic nitrogenous waste from the body. When the glomerular filtration rate shuts down during dehydration, waste products cannot enter the tubule through the normal front door of arterial filtration. Instead, the tubules must actively pump, or secrete, these toxins directly from the surrounding blood across the cell membranes and into the tubule lumen. The renal portal system supplies the massive volume of raw venous blood required to subsidize this high-energy secretion process, delivering the waste directly to the active transport cells. By combining targeted arterial shutdown with venous portal delivery, the avian kidney decouples water conservation from toxin removal. The precise nitrogenous waste birds are pumping into these tubules is uric acid. Mammals take a completely different chemical approach, converting and excreting their nitrogenous waste as urea, a highly water-soluble compound. Because urea remains dissolved in liquid, it is highly osmotically active. It physically traps large volumes of water within the tubule, forcing that water to be excreted alongside the waste. The avian reliance on uric acid bypasses this trap entirely because uric acid is highly insoluble in water. As the tubule reabsorbs water, the remaining uric acid rapidly exceeds its solubility limit and physically precipitates out of the fluid. This precipitation breaks the osmotic trap. Once the uric acid crystallizes into solid form, it drops out of the solution and no longer holds on to water molecules, allowing the kidney to reclaim nearly all the surrounding liquid. By the time this waste reaches the ureter, it is no longer a true liquid. It is a dense, white, semi-solid colloidal suspension. Converting waste into a solid grants birds massive water independence, ensuring they can continue to clear nitrogenous toxins from their blood even during severe dehydration. This diagram shows the anatomical layout of the lower intestine, confirming that the avian excretion process does not end at the kidney. The final, crucial step happens directly inside the gastrointestinal tract. The solid nature of uric acid presents one final risk. As it precipitates, it physically traps valuable electrolytes and peptides inside its crystalline matrix, resources the bird cannot afford to lose. When ureterial urine drops into the cloaca, it is not immediately excreted. The tract's muscular walls engage in retroperistalsis, actively propelling the urine backward and upward. You can see the flow path here, moving up from the urodeum into the coprodeum, colon, and ceca. In these chambers, the intestinal walls act as a final filtration barrier. They actively strip the remaining sodium, chloride, and water from the uric acid matrix. This process of intestinal transport is highly dynamic. Hormones like aldosterone upregulate the absorption rate in direct response to the bird's immediate dietary salt and water intake. Ultimately, what remains to be expelled into the environment is a highly concentrated, dry white paste that preserves maximum biological resources. The success of the avian renal system stems from a three-part integration of specialized nephrons, portal blood shunts, and gastrointestinal water reclamation. In combining these mechanisms, birds match mammals in overall water conservation efficiency.